Good morning, evening, afternoon, or whatever time it happens to be that you're watching this video. Today is Tuesday, and today I wanted to talk to you guys a little bit about a very, I, what I think is a very interesting phenomena, and something that comes up a lot in popular culture and popular science, and that is radioactive decay. Um, to understand radioactive decay, we from what you've learned in chemistry and what we've talked about this year, I think we have a good basis to start talking about radioactive decay. There's only like one thing that I wanted us that we need to kind of review before we talk about radioactive decay, and that's this definition thing about isotopes. So um, if you think back to like your chemistry class, you might have talked about, depending on how far y'all may have gotten, you might have talked about isotopes. And an isotope, isotopes are basic is a word given to the same element. So we're talking about the same element, but different numbers of neutrons in the nucleus. So there's these things called isotopes, and that's basically when you have the same element but different numbers of neutrons in the nucleus. So if you recall from your chemistry class, the element, what makes an element unique is the number of protons. If you're looking on the periodic table, what makes an element unique is the number of protons. If you look at element number 1, that means it has 1 proton and that's hydrogen. If you look at element number 2, that means it has 2 protons and it's helium. All helium, anything that's helium is the element helium, and it would have 2 protons. Anything that's hydrogen is the element hydrogen, and it would have 1 proton. But the number of neutrons inside that element can change for any given element, and that's what makes something an isotope. So we can talk about that. We can give an example to talk about that, and that example is with the naturally occurring isotopes of helium. So there's 3 naturally occurring helium. Sorry, I said helium, but I meant hydrogen. Naturally occurring hydrogen isotopes. Isotopes. And we can just draw pictures to illustrate them. So the most simple form of helium, I keep saying helium, the most simple form of hydrogen is just 1 proton and 1 electron. So you've got 1 proton and 1 electron, so that's hydrogen. This notation is used for isotopes. Basically, what's up here is so I guess we could talk about this in a generic kind of way. So we've got your number, your atomic mass number, you've got your number of protons, and then you've got the element. So X is the element symbol, like hydrogen, carbon, fluorine, etc. N is the number of protons and neutrons. So that's also your atomic mass number, the protons and neutrons. And then Z is just the element number, or I forget the chemistry word for that, but basically I just know Z as the number of protons. So that's kind of what this notation is telling us about. And if you're talking about just this plain old hydrogen with 1 proton and no neutrons, this is what we would just call normal hydrogen. But there are 3 isotopes of hydrogen. And so the next isotope is it's an isotope, so it's the same number of protons, but you just have a different number of neutrons. So there's another isotope of hydrogen that has one proton and one neutron. So because the number of protons and neutrons is now 2, we would write this like this. The way we would use this notation is that there's a proton and a neutron, so we've got a 2, it's hydrogen because there's that's the element uh, symbol because there's one proton in the nucleus. And this isotope of hydrogen is called deuterium. Deuterium. This is a very expensive element, and it's or isotope, and it's very useful in some nuclear reactors. Actually, it has some very useful properties in certain kinds of reactors that they use specifically in Canada. Um, and then there's a third isotope of hydrogen, and that's just you're basically just you're just changing the numbers of neutrons, right? So this third isotope of hydrogen has 2 neutrons in the nucleus, and so there's 3 particles in the nucleus in total. So this would be written out like such, 3H1, and the name for this isotope is tritium. Make some room. The name for this isotope is tritium. And the thing that's very interesting about these, so that's isotopes, right? These are 3 different kinds of isotopes of hydrogen, where the only thing that's different is that there's a different number of neutrons in the nucleus. Same number of protons, so it's the same element. We use the same symbol, but we are changing the number of uh, neutrons in the nucleus, which is what makes these different isotopes. Um, so, and the thing that's interesting about these different isotopes is that some of them are stable and some of them are unstable. And what tends to happen is that as you make the nucleus larger, the atom itself or the isotope itself becomes unstable. So if we're talking about hydrogen and deuterium, these are both stable, but tritium is an unstable element or an unstable nuclei. And if it's unstable, basically what we want to know is that some atoms or some isotopes are unstable. And they're unstable for a variety of reasons, but it's mostly based on their nuclear structure. These isotopes are unstable, and what all things in nature want to do is they want to achieve some sort of stability. Like if you have a ball on the top of a hill, that's unstable, and that ball wants to come to a more stable position. It wants to roll down that hill. Whenever you have these unstable isotopes, they want to become stable and they will do whatever they can to achieve that. And for these unstable isotopes to achieve stability, they will actually eject or emit particles from their own nucleus. And those particles, depending on what the isotope is, the particle that they emit can be different. They could be emitting an electron, they could be emitting a positron. Um, they could be emitting a um, a helium nuclei, or they could be emitting electromagnetic radiation. Or another way of saying that is just they could be emitting particles of light. So some of these unstable nuclei, to achieve stability, they will actually sacrifice parts of themselves, kick them out of themselves. They will emit these particles from their own nucleus in order to achieve that stability. And this phenomena is called radioactive decay. This is radioactive decay. Isotopes that do this, isotopes that decay, um, and go through this process are said to be radioactive. These unstable nuclei, they will, to achieve stability, they'll be kicking out some part of their nucleus in order to become more stable. The process, or that process, is called radioactive decay, and whenever something is doing that, it's said to be radioactive. And then the particles that the things are emitting is what we call is what we would refer to as the radiation from that decay. Um, so that's probably the last thing to mention, is that the emitted particle is what we would refer to as radiation. That emitted particle is what we would call radiation. And so, to kind of illustrate that, because we had already talked about the different isotopes of hydrogen, we can illustrate this process for the tritium nuclei. And excuse me. And for tritium, um, the specific mode of decay is called beta decay. So this is what's going on with beta decay. Um, you've got some nucleus, like we've got that tritium nucleus, so it's one proton with two neutrons inside the nucleus. So this is our tritium atom, and in beta decay, what happens is actually very, very interesting. These are our neutrons, right? And with beta decay, something very interesting happens with this neutron. Basically, this neutron is actually going to become several different things. If you think about the neutron, it has zero charge, and it's a fairly large particle. The neutron actually has more mass than the proton. So what's going to happen with this neutron spontaneously in beta decay is that this neutron is actually going to become three different things. This neutron is at some point, it's randomly going to break up, and it's going to become a proton, which is positively charged. It's going to also become, part of it is going to become an electron, which is negatively charged, and part of it is going to become what's called an anti-neutrino, which is which is another kind of particle that has no charge. So basically, that neutron becomes a proton, electron, and an anti-neutrino. That is what happens with a beta decay. This neutron randomly, for a very unknown, very strange reason, this nuclear structure is unstable. To become stable, this neutron, one of these neutrons, will spontaneously transform itself into these particles. And notice that you had zero charge at the beginning, and in total you have zero charge at the end, because 1 minus 1 is 0. So I started with zero charge, I end up with zero charge, so charge has been conserved. But what has happened is that the neutron that was here has now become a proton, an electron, and this anti-neutrino. Because this is all happening inside of the nucleus, this electron is negatively charged, and it finds itself inside of a nucleus next to two protons. So what's going to happen to that electron? This electron is negatively charged, surrounded by protons, that electron is going to get kicked out of the nucleus. So this electron gets emitted from the nucleus. And that's what we would, that's in this example, that emitted electron is what would be the nuclear radiation. Right, we had talked about how the emitted particle is your radiation, so this electron is being emitted from the nucleus, and that would be our nuclear radiation in a beta decay. The thing that's emitted is this electron. So basically, uh, the isotope of tritium that we started with has transformed itself into a new element, right? Because we've gained a proton inside of the nucleus. So now inside of the nucleus, we have 2 protons, the remaining neutron, and we have some electrons. So now we've got 2 protons. Sorry, we've got 3 particles inside of the nucleus. We've got 2 protons, so that means our element is now helium. And we've got 2 protons, so we would change this number to a 2. And then we've also got that electron that was formed, and we've also got that antineutrino that was formed. So this is what happens in beta decay. Some radioactive isotope has a neutron inside of it, and that neutron becomes a proton, an electron, and an antineutrino. That electron and the antineutrino get kicked out of this nucleus, and because you've gained a proton, now you've transformed your element. You started with hydrogen, and you've ended up with helium. So that's something that's very interesting as a consequence of radioactive decay, is that you can actually get elements transforming from one into another, hydrogen becoming helium. And so that's something very interesting to note about radioactive decay. And basically all decay modes except gamma decay result in this process, result in one element being transformed into another. All decay modes except for gamma result in one element being transformed into another. And we give that kind of we give that a name, and that is called nuclear transmutation. Nuclear transmutation is the process by which, in a radioactive decay event, a element gets transformed from one form into another, from one element into another. So that's a very interesting consequence of radioactive decay, is that you can actually get elements transforming from one to another. Um, so now that we've kind of talked about radioactivity, and we've got a little bit of basis for what's happening, at least for some of these decays, for some of these modes of decay, whenever we come back in the next video, I'm going to talk to you guys a little bit about a application of radioactivity, and also a very common thing that's discussed about radioactivity, which is half-life. So that's what we'll talk about next time. Thank you for your time, and have a great day.